Alrighty guys, we're going to go ahead and get started with our current, voltage, and resistance notes. And these are the basics of our circuits. So first thing I want to talk about is voltage. And we're going to say that voltage is the charge pusher. And by charge pusher, we're talking about electrons, right? Electrons are the charges that are getting pushed throughout these circuits. And voltage is also known as the energy provided to the circuit. So when we think about voltage then, types of voltage sources would be batteries and outlets. Because when we need energy, what do? We plug our phone into the outlet. When we need energy in our remotes, what do? We grab some batteries and put it in our remotes. The symbol for voltage is going to be the capital letter V, and the units for voltage are volts, which can be abbreviated by the capital letter V as well. Now let's talk about current. And we're going to say that current is the flow of charge within a conductor, or how fast charge is moving. And that charge again is referring to electrons. And if we think about current in terms of water, right, it's how quickly that water is moving. Charge will only flow if there is a voltage source. So if we don't have any voltage source or anything supplying energy, we don't have any charge. Just like if we don't have any water, the water can't move. Makes perfect sense. The symbol for current is the capital letter I. And the unit for current are amps. And amps can be abbreviated with a capital letter A. Resistance. So resistance is how easily a material lets current flow through it. Resistance affects the speed of the current. So think about just resistance in real life. If you are resisting to do something, then you are not allowing something to happen. So the more resistance a object has, the less likely there is that current can flow through it. The symbol for resistance is the capital letter R. The units for resistance are ohms, and ohms are abbreviated with the omega symbol. Again, if we're thinking about resistance, what type of objects do you think have very high resistance, which means that they don't allow electricity to flow through? Well, that would be insulators. Insulators are going to have extremely high resistance because they don't want electricity to flow. So plastic, rubber, anything that will not allow electricity to flow. And things that have very low resistance, well, that's going to be conductors because they want to allow that electricity to flow through it. And a conductor, like we said before, could be metal, such as copper wire. Any type of metal will have low resistance, which means that it is a conductor. So let's talk about the relationship between voltage and current, assuming that resistance is remaining the same. We can say that if the voltage in a circuit increases, the current will increase. And that just means as we're supplying more and more energy to that circuit, the current is moving faster and faster. If the voltage in a circuit decreases, the current will decrease. So if we're taking energy out of that circuit, the current will move slower. So if we think about this really simply, we could argue that because there's less voltage, there's less electrons, and because there's less electrons, there's less movement in the circuit. This is a direct relationship, which just means that if resistance remains the same, increasing voltage will increase current, and decreasing voltage will decrease current. Let's take a look at resistance and current relationship, and let's assume that voltage now remains the same. Well, if the resistance in a circuit increases, meaning that it is harder for those electrons to move, the current will decrease. And that makes perfect sense because we just said that increasing resistance means that we are making it more difficult for those electrons to move. If it's more difficult for them to move, they're going to move slower. And that's why the current decreases. If we decrease the resistance now, meaning that we make it easier for these electrons to move, the current will increase. And if we just thought about it really simply, Let's say that we had everybody exiting the school out of one really, really small door. Well, there's a lot of resistance there, right? That door is super tiny and it's creating a bunch of resistance, which means that the current or the people are moving very slowly out of the door. Now, instead of us having a very, very tiny door, let's replace that and make it a huge garage door. Well, that garage door is ginormous, which means that there's not really that much resistance for these people to leave. What does that mean? That means now people can move faster. Because there's less resistance, the current or the people in this situation are able to move quicker. This is an inverse relationship, meaning as resistance increases, our current decreases, and as resistance decreases, our current increases. Here's a quick diagram just showing that to help you guys visualize it. Right here we have voltage on the left, we have resistance up top, and current in the middle. And we can see that voltage is pushing that current through the circuit, but resistance is slowing it down. So in this case, we see that there's a lot of resistance because that current is barely moving. And what does that tell you? Well, that just tells us that if there's a bunch of resistance, like tons of resistance, current won't even be able to move. And if there's no resistance, then the current will be able to move very easily, super quickly. All right, now that we've talked about voltage, resistance, and current, let's start talking about the pieces that make up a simple circuit. And right here, I have them all outlined. The important parts are going to be a battery, a light bulb, a voltmeter, an ammeter, a resistor, and then I'm going to show you two examples of what those look like. So the diagrams I'm going to show you are schematic diagrams, which means that it's the universal symbol of what people use to draw these objects. So the first one is a battery, and a battery just looks like the following. It is one horizontal line with a break in the middle and two vertical lines. This just symbolizes one battery. If we wanted two batteries, we would just add another one on top of it. And we'll get to that later on in the unit, but just know that the battery looks like this. And the important thing to note too about the battery is that this part right here, the big end, is the positive side of the battery. And the small end is the negative side of the battery. Next, we have a light bulb, and a light bulb just kind of looks like a circle with a squiggly inside. The next one we have is a resistor, and a resistor is just kind of like a lightning bolt. It's alright if you just want to use the resistor symbol for a light bulb, because a light bulb is a resistor. But the reason it has its own symbol is because it's a very common household appliance that everybody has and everybody uses, so it has its own symbol. A light bulb is a resistor. A resistor is really anything that uses up energy or requires energy. Next, we have a voltmeter, and we'll talk about what a voltmeter is later on more in our notes. But just for the sake of these notes, a voltmeter is exactly what it sounds like. It is a meter that measures volts. And that is just a circle with a V in it. An ammeter is a meter that measures amps. So in other words, it is a meter that we use to measure the current in a circuit. And again, we'll talk more about that in later notes. So here's an example of a circuit with one battery and a light bulb. And here we see a bunch of these lines that we didn't really talk about. But if we had to guess, we could see that these lines obviously represent wires, because we need a wire connecting from our battery all the way around to our light bulb and then back to our battery. The only way a circuit is going to work is if it's a closed loop. You cannot have an open loop circuit because the electricity will not flow. You need both ends of the battery touching in order for the circuit to work. Now let's take a look at a circuit with two batteries and one resistor. And here we go. Just like we said, we have these two batteries stacked on top of each other. So we notice that the positive side is stacked on the negative side. And if you guys have ever replaced the remotes in your batteries, you'll notice that too. How those remotes, you stack the batteries on top of each other, positive to negative. Here's our wire. And then here's our resistor, just like we said. and again it connects back over to the battery. So main takeaways here is that these are important schematic symbols that we'll be using when we describe circuits and when we make our own circuits in class.